Today we look at performance tuning considerations in Hadoop. So Hadoop is a massively like huge data set application, and like dealing with large amounts of data can cause multiple errors. Like um, when we want to tune the performance of Hadoop ecosystem, one thing we need to think about is memory tuning. So if you look at if you have a Cloudera implementation of Hadoop, there's a in the Cloudera manager you'll be able to monitor swap memory. So swap memory, if you look at the swap memory and if there is like excess swap memory utilization, you can use the mapred.child.java.opts property, and you can reduce the amount of RAM that is allocated to each task. And in the mapred.child.java.opts, if you can see that it's available in mapred.site.xml, and you can actually update that to be xmx 2048m. Typically it's xmx 10224m, which is 1024 megs. You can change it into 2 gigs, which is 2048m. So that would any change in that would allow you to like not run into low swap memory. So whenever you see that the swap memory utilization is high, you can increase that in that property in the mapred site XML. The option name is mapred.child.java.opts. Um, you can also think about a lot of bottlenecks in Hadoop come with disk write and read. So the IO performance is something we need to think about. If you have a Linux file system, and like Linux has a checkpoint for each file, so as soon as you finish writing the file, it checks the checksum, last access time, the created time, the user, all those things is a checkpoint. So in Hadoop, we don't do all that. So to achieve a better IO performance, we disable the checkpoint in HDFS. So HDFS supports write once, read many times model, which is also called a worm model. The applications will be able to access the HDFS data in a random fashion. So the difference between Linux and HDFS here is that in Linux we always have a checkpoint after the file is written, but in HDFS, to actually get better IO performance, we always disable the HDFS checkpoints. The next one is the mount points for data node or data directories should be configured with the NOA time option to ensure that the metadata is not updated by name node every time the data is accessed. The mounts for MapReduce storage and DFS, when mounted with the NOA time option, deactivates access time tracking, rendering the enhanced IO performance. So if you want to have a better IO performance, then like use the NOA time option so that it deactivates time tracking. The next one you can do is there are two configuration parameters, mapreduce.local.dir and dfs.data.dir. You should set those such that they point to one directory on each of the disks. So that will help that it uses the better overall IO capacity. So there are two different directories, like the mapreduce.local.directory and the dfs.data.directory. If you make sure that they point to one directory on each of the disks, that will help better IO performance. The last thing in this slide is don't use LVM and RAID on data node. So these are configurations that are how your disks are set up. So this is more to do with hardware. So don't use like RAID hardware or LVM hardware. those things are bound to reduce the performance. So use a like large 1 terabyte SSD, but using RAIDs or LVMs or um, like task tracker machines, they reduce the Hadoop ecosystem performance. The next one we're talking about is minimizing the disk spill. So like when we have a map output, we write all that down into a disk. So that like that is all that disk IO is a performance bottleneck, because writing and reading from a disk is about 10 to 100 times slower than writing and reading from a memory. So what we can do is you can ensure that the mapper for your MapReduce uses 70% of heap memory for spill buffer, and you can compress the mapper output. So instead of writing it uncompressed, you can compress the mapper output. So let's look at compression itself. So when the map output is very large, there are some compression libraries, compression formats like LZO, bzip, snappy. You can use any of those compression techniques to actually compress and write the records out um, when the map output happens. And you can configure that under the parameter map produce.map.output.compress, and then you can set that to be true. And in under the map produce.map.output.compress.codec, you can set up whatever compression technique you use. I've used Snappy, which seems to be used a lot using Parquet files as well. So that is pretty typical of what I've seen. And what you can see is that like when we use something like LZO, so in this example, they've seen what happens if you use a LZO data compression, and you might initially see that the CPU takes longer because it has to also do a compression before it writes. But because it has to write 1 GB instead of 3 GB of data, in this example of whatever data they've taken into consideration, it shrunk it by 1/3. So it wrote 1 GB instead of 3 GB. So the disk IO has been considerably reduced in this example of compression. Um, Another performance consideration you can and you should use as a programmer is number of mapper or reducer tasks. So controlling the mapper or reducer tasks is a heavy input into how you can perform better. So every map or reduce task usually takes 40 seconds to complete execution, and there's a large job that needs to get executed. Like you want to use all the slots that are available in the cluster. Like tuning the number of mapper and reducer tasks is pretty important. You need to know how many other jobs are running at the same time, and how many like slots are available in the cluster. That helps tuning this. So the first point here is if the job has more than 1 terabyte of input, then to ensure that the tasks are smaller, then the data set input the block size of the input data set should be increased. So instead of 128, rather use 256 or 512 MB. And how do you configure this? There's a block size property, dfs.block.size. Use that to control what your block size would be. After you change the block size, the original data can be removed. So whenever you run a map produce job, say you have more than 1 TB of input, then ensure that for that job you send a property dfs.block.size, and you set the value to be like higher for that particular job. If the MapReduce job on the Hadoop cluster launches several map tasks, say you have multiple map tasks, wherein each task completes in just a few seconds. So it's a like 10,000 jobs that get 10,000 map tasks that get generated, but each of them finishes in under like 30 seconds. Then what you would rather do is you reduce the number of maps being launched for that application. So the configuration of a Hadoop cluster you can change such that you can reduce the number of maps being launched. That would actually help the performance, overall performance. What this ensures is that the task load on the application master is reduced while allocating the desired resources. The last point here is setting up and scheduling tasks require time overhead. If a task takes less than 30 seconds to execute, then it's better to reduce the number of tasks. Reusing the JVM is a good alternative to this problem. Let's talk about a combiner. So, should we write a combiner? That's another thought process we have to think about while considering Hadoop performance tuning. Like, not only the compression, we also have to think about combiner or reducer. So that also reduces the amount of data that needs to be transferred, and that can actually prove that much less data is transferred in the pipeline, and then that makes the job much faster, resources usage much lower. If the job performs large shuffle, that is like the records get written from one node to another because they need like to combine similar outputs together. So those kind of jobs where you perform a large shuffle, the map output is several GBs per node. So each node has like several GBs, and you're shuffling huge number of GBs between nodes. And say you're doing an aggregation sort, you have to write a combiner so that you can actually optimize the performance. So combiner acts as an optimizer for the map reduce job. So if you do the combiner, that helps the map reduce job run faster. It runs on the output of the map phase. So the combiner runs after the map phase and reduces the number of intermediate keys being passed to the reducers. So before the reducer runs and after the map runs, the combiner runs, and it maps it to the right nodes. So the number of intermediate keys being passed to the reducers comes down. It also reduces the load of the reduced task in processing the business logic. So essentially, if you can reduce the number of shuffles, if you can reduce the number of items being passed through the data pipeline, those two things are pretty useful, and for that we typically write a combiner. Okay, the second last thing we're looking at today is skewed joins. For skewed joins, whenever you use a standard join, like you write a pig query or a hive query, or you write a MapReduce tool, when you join like table 1 and table 2, you what it essentially does is it looks at the keys in table 1 and the foreign keys in table 2 and sorts them and matches them together. Like where this can cause a lot of skewness, that is 80% of the data is going to like say one reducer, or like most of the data is going to one reducer. So that is what a skew is. If there's huge amount of data for one single key, for example, if you're joining based on last name and a lot of people have the last name Smith, then that would mean we are having a huge skew in the data, and that would mean all the names that have the last name Smith would come into one um, uh, reducer, because that one reducer processes all the like Smith last name records. So that will have a huge number of records it's processing. So that's when it's called a skew, and skewed join uh, happens at that time. So try to avoid the skewed join as much as possible. So to run skewed joins, what Hadoop does is it computes a histogram to find out which key is dominant, and then the data split based on its various reducers to achieve optimal performance. Okay, that's all I have for today. Thank you so much.